that is positive 1. And as you keep going out, you get further and further. So both negative 1 and 1 are the same distance from the mean. They're just in opposite direction. So plus 1 is 1 standard deviation above the mean, whereas negative 1 is 1 standard deviation below the mean. Okay. So if they do give you a question on mean, standard deviation, or variance, and they give you a couple marks, they've got to keep the numbers fairly simple, because of course you can't get a standard deviation of 6.025 without a calculator. I know there was one exam, it was a couple years back now, I'm not sure if it was 2 or 3 years, but they did complain that the exam was really brutal. And it wasn't so much that the numbers, like that the questions were brutal, but it was like the numbers on the exam. They said there was a lot of mental math that year. So lots of fractions and things. So make sure you do practice doing mental math. Don't get your calculator at all, right? For practice, because you'll get better at mental math if you do more of it. So find the mean and standard deviation. So I have 5 numbers. My marks are student 1, 2, 3, 4, 5, 80, 60, 70, 70, 20. Okay, so your mean, x bar, would be the sum of all the x's divided by n. So we'd have 80 plus 60 plus 70 plus 70 plus 20 all over 5. All right, go ahead. No calculator, what would you get here? Okay, so we've got 140 here. 140, so plus 20 is 160, so that's what, 300. So 30 divided by 5 is 6, so 300 divided by 5 would be a mean of 60. Okay, so the standard deviation, S, is the square root of the sum, each mark minus mean squared, all over 1 less than n. So if n is 5, we divide by 4. Okay. And if we want the variance, we just wouldn't square root it. Okay, so the variance would just be without the square root. So each mark, so 80 minus a mean of 60 squared. Second mark, 60 minus 60, we get lucky there, that's just 0, obviously. And then 70 minus 60 squared. And 70 minus 60 squared. And 20 minus 60 squared. So we take that answer, whatever it is, we divide it by 5 minus 1 is 4. If we don't square root it, it's the variance. If we take the square root of it, then it's going to be the standard deviation. So in your head, well, 80 minus 60 is 20. 20 times 20, or 20 squared, is 400. You don't need the 0. 70 minus 60 is 10. 10 squared is 100. 10 squared is 100 again. 20 minus 60 is negative 40, but a negative squared is still positive. So 40 times 40 is 1600. Okay. So next step would be what? Simplify this, what do you got? So 16, so that'd be 2,000, 2,100, so 2,200 over 4. So 2200 over 4 would be the variance, and now I have to root it to get the standard deviation. So if I think about that as, that's 1100 over 2, so root of 550. And the variance would be 550. Okay. And you note this year they asked for the z-score of the mean. The z-score of the mean, so they would do the mean divided by the standard deviation. So that was kind of a weird new calculation. So you won't see that on any of the practice tests, because they normally do it as, each mark minus mean over standard deviation for a z-score. Okay, so z-score of the mean. Okay, so for relative standing, we would just take whatever the person's mark is minus the mean of that particular test all over standard deviation. So I'll do one person for you, and then, you can finish the rest later. So a z-score or a relative standing, mark minus mean all over standard deviation. So if this person's mark was 60 minus a mean of 67 all over standard deviation of 10, that's negative 7 over 10 or negative 0.78. So that would mean that this person scored 0.7 standard deviations below the mean, right? They scored below the mean mark. And the z-score is the number of standard deviations below the mean that they scored. So if it was a plus 0.7, that would mean they scored 0.7 standard deviations above the mean. Okay, so I'll let you try B and C. Ask me if you have any trouble. And of course, if you have to rank them from largest to smallest, then you can do that based on your 3 answers. Okay. The mean and standard deviation of last year's midterm were 62 and 8 respectively. This year, the mean and standard deviation were 58 and 16 respectively. Samuel scored a 90 on this year's exam. What would be his equivalent grade on last year's exam? Okay. Take a minute or two and see what you can come up with here. What do you think? Okay, so if we look at, the z-scores, if the marks are equivalent, then they would have the same z-score. Or same relative standing. So for last year, he got a mean of 62 and a standard deviation of 8. On this year, he had a mean of, let's see, where is it? Okay, this year the mean was 58 and standard deviation of 16. Okay. Now it says his score is 90 on this year's. So that's Samuel's mark. So let's see. Z is x mark minus mean mark over standard deviation. So his z-score is 90 minus 58 over 16. So that's 32 over 16, or a z-score of 2. So on average, 2 standard deviations above the mean. So now, if we go to convert, and to find this equivalent mark on last year's, then we put z as 2 on the left, and we're solving for his mark, which is his x, minus the mean on this exam was 62 over standard deviation 8. So cross multiply, 16 is x minus 62. So his mark is 16 plus 62, so 78. Okay, questions? Okay, so data benchmark values. So you don't do actual t-tests in this course like you would in a stats course, but we can, talk about just the basics here. So if you need a value to compare experimental results to be able to identify type 1 and 2 errors, the value they often use is t, is the absolute value of the mean over the standard deviation. X bar is sample mean, S is standard deviation. You can run the experiment thousands of times and check for errors. So if you can create this new experiment by pulling out these trials from a normal distribution where E of X is the perfect value and variance of X is S squared, then the T equation would be X bar, so mean, minus E of X all over standard deviation over root N. This would be our t-test that we can use in stats. This is a more simplified version. So the t is the square root of n times t. And we knew that our capital T was up there, the mean over S. Okay? And n is the number of trials in the experiment. So if the sample mean is 5, well, that's X bar. And the sample variance is 9. So be careful, that's not S, that's S squared. So we would have to square root it. And you perform 10 trials. What is the student's t-test benchmark value? So the t is square root n times the mean over standard deviation in absolute value. So that'd be square root 10 and then 5/3, which is really just 5 root 10 over 3 as a, fraction. Okay, so you talked about uniform random variables. We talked about them a little bit in the continuous section already, but you can also talk about them in terms of type 1 and 2 errors. So, from the assignment. So a type 1 error is we conclude that there is an effect when there isn't. Type 2 error, we conclude there's no effect when there is. Both are false, of course. So say our data has a mean of -0.5 and a variance of 3. If we have false data, we have that E of X is 0, so no effect for type 1 error. So if we look at the graph of z-scores, here -0.5 rarely occurs if E of X is 0, and therefore E of X probably isn't 0 at all, right? Because this is -0.5 here. If we got this graph instead, -0.5 here, this happens due to random sampling even when E of X is 0. So we already talked about, generating random variables, pseudo-random variables. So if we're looking for a random variable from some negative a to a, well, here we're generating numbers on uniform random variable from 0 to 1, subtracting 1/2 from each number, and then multiplying by this constant 2a. Now, if you look at a graph that goes from negative a to a, let's say it's, -1/2 to 1/2, we know this is area, length times width is 1. And so if we know that, here, if we've got, from negative a to a, well, then if we look at this, if this length is really a and a is 2a, right? Because if it's a here and negative a here, it's a total of 2a units long. If this is 0, and then their width, well, if area is length times width and the length is 2a, then if that has to be 1, your width has to be 1 over 2a, or your height, whatever you want to call it, of your rectangle. So the variance is integral from negative a to a of f of x times x minus x bar squared. The mean, we're saying since a type 1 error means x bar is 0, we can put that in. And you've got your integral, 1 over 2a, integral from negative a of x squared. And the variance they told us was 3. So if we set the 3 equal to this, then we can solve for the value of a. And of course, integrate top number subbed in minus bottom number subbed in. So that's similar to something that you had to do for the assignment, except of course you had to use Python for parts of it too, right? Okay, so I think after that is a practice test for probability. So that's D, and then E is where we're going to flip to next, which is on 212, which, to be honest, they pretty much removed all the easy vector stuff from the course. So you used to have a couple sections on vectors with all the stuff that you had to know, but they took it all out. So there's not much left on vectors, right, that you talked about. So you did talk about, for example, the magnitude of a vector. So every vector, of course, has a magnitude and a direction. And if we want the magnitude or length of a vector, then it's the distance from the origin. So if our vector is in our three components, A1, 2, 3, and then the magnitude is denoted by 2 lines. In a really old exam, you might see this. That still means magnitude because it's a vector. In the older exams, so they used to use 1 line. I always prefer 1 line for absolute value and 2 lines for magnitude, but in this course, they've switched back and forth a million times. So just in case you see that. If it was just absolute value, it wouldn't be a vector, right? Like absolute value of -5 is 5, for instance. So the magnitude would just be square root and then square all the components and add them up. So A1 squared plus A2 squared plus A3 squared under a root. If it's exactly 1, it's called a unit vector. Okay? So anytime your magnitude is 1, it would be a unit vector. So if you had to do the magnitude of a vector, if we have vector u, we just do square root -1 squared plus -2 squared plus 3 squared. And if it was a vector v, square root -2 squared plus -1 squared plus 1 squared. So any negative squared is positive. So that's just 4 plus 1 plus 1 under a square root, or square root 6. Okay, so go ahead. What's your magnitude of W going to be here? So we've got square root and 5 squared plus -1 squared plus -2 squared. So 25 plus 1 plus 4 under square root, or square root 30. If we want to do scalar multiplication, so multiplying a vector by a constant, then we just multiply the constant by all the components. So 3u would be 3 times -1 is -3, 3 times -2 is -6, 3 times 3 is 9. If you multiply by a negative number, a negative scalar, then that new vector is going to move in the opposite direction of the old one. So something like -2u down here negative 2 times vector u, 2, 4, negative 6, then that's going to be moving in the opposite direction. So if we wanted something like this, then we would kind of treat it like a bracket. So I would do the inside first. So go ahead, take vector w, you're going to do negative 3w, and then you're going to magnitude the answer. What would it be here? Okay, so we'd have magnitude, negative 3 times w, 5, negative 1, negative 2. So that's negative 15, positive 3, positive 6. So square root, negative 15 squared, plus 3 squared, plus 6 squared. So 225 plus 9 plus 36. That's a little bit big to do in your head. So, yeah. Okay, so example 3 here, what would you do? Okay, so we have magnitude. We take vector A, 3, negative 4, minus 2 times vector B. So I would say leave the 3, negative 4. You can either leave this as subtract and multiply by 2, or you can multiply the negative 2 in and change it to plus. It doesn't matter. It'll be the same answer. I'm going to do negative 2 times everything. So that'll be positive 4, negative 8. So magnitude, to add vectors in the same spot, we would just add, the same component spot. So 3, negative 4 plus 4, negative 8. 3 plus 4 is 7. And then we've got negative 4 plus negative 8 would be negative 12. So magnitude is square root 7 squared plus negative 12 squared. So final answer, root 49 plus 12 squared is 144. So root of 193. So C. So to add, we obviously just add the numbers in the same spot, okay? So to add vectors, you're just adding the same component. But for subtraction, make sure you're adding the opposite, so watch your signs. You can take a look at the pictures here. There's parallelogram method, and then there's triangle method of adding. But basically, on 216, like if you want to add vectors, if you want to do v plus w, let's say, then we've got to take negative 2, negative 1, 1, plus 5, negative 1, negative 2, and you're just adding numbers in the same component spot. So negative 2 plus 5 is 7. Negative 1 plus negative 1 is negative 2. And 1 plus negative 2 is 2. Oh, it's negative 2 plus 5. No, I thought it was 2 plus 5. Sorry. So negative 2 plus 5, that would be 3. So 2 in my brain here. So 3. And then negative 2. And then 1 plus negative 2 is negative 1. So if you tried, let's say D, let's do that, and then we will just take a break before we get on to the rest. I believe that's it for operations of your vectors, because, yeah, everything else, no dot, no cross, none of the other stuff now. Okay, so what do we get here? So that would be -3, -6, 9. I'm going to multiply the -5 in. So it'll be +10, +5, -5. And add up the same component spots. -3 plus 10 is 7. -6 plus 5 is -1. And 9 plus -5 is 4. Okay. So come back at 8:05 and we will carry on, okay? Have a good break. I'll see you back soon. done for tonight, so try and make it through. Just another hour to go, okay? So we'll switch back to page 217. So the last thing in this section is linear combinations here. So on page 217, so here we have, we're going to use this concept later, but if V is a linear combination of vectors u1, u2, then we can say that V is some constant c1 times one vector plus c2 times another vector. So if we want to find the constants here, we can just make an equation from, the top of each, and then the equation from the bottom. So c1 times 1 is c1, c2 times 2, so plus 2c2 equals 17. And then the bottom would be c1 times 3 plus c2 times 4 equals 39. So 3c1 plus 4c2 equals 39. And to solve these, we'll be doing this kind of thing at the end tomorrow, but we would need to either substitute or eliminate. I usually use elimination. So we either need the same number in front of c1 or the same number in front of c2. So it doesn't matter which one you do. These are like a 2 and a 4. I'd probably just multiply this whole equation by -2. Make sure you do it to both sides. So this whole equation times -2 would give me -2c1 minus 4c2 equals -34. So if we copy down the second one, now because they're opposite signs, we can add to get rid of them. If they were both positive or both negative, then we'd subtract the equations. So this is adding -2c1 plus 3c1, that's just 1c1. So that's easy. -34 plus 39 is 5. So that's my c1. I can put it back into either equation. Number one is probably slightly easier. So c1 plus 2c2 is 17, and then I can get my c2. So 5 plus 2c2 is 17. Bring the 5 across. So 17 minus 5 is 12. So if 2c2 is 12 and I divide both sides by 2, then c2 is 6. So my constants are c1 is 5 and c2 is 6. Okay, so we talked about that in terms of linear combinations, but again, it's going to come up tomorrow. Okay, so flip to the next section on vector fields. Any questions before I flip here? Okay, so vector fields is on 219. So vector field is, going to be a collection of arrows, right, representing the various vectors. And so if we want to draw the vector field for a recurrence relation, xt plus 1 equals a x of t, then we'll draw the arrows starting at v and ending at av. Because there's so many, of course, we can use computers to draw them, right? So in here, like I listed a website where you can, practice drawing the different vector fields. So they're important in making long-term predictions. So if we have f of x equals ax, and representing it graphically here, then we're going to draw the vector ax as an arrow applied to a point x. And any linear function is going to have this distributive property that a times, constant a times vector u plus constant b times vector v, we can multiply it out. And we can say, it's kind of confusing, right? Capital A times little au plus capital A times bv. But we can put the little a out in front because, a is just a constant. The number can come out in front, and then plus b out in front of av. And then we'll talk about the vectors a times u plus a times v in the next section. So those will be our eigenvectors, right? We'll talk about eigenvectors and eigenvalues tomorrow. So If we want to talk about f of x being linear, then it's linear if it preserves a linear combination of vectors. So if f of some constant c1 times vector x plus some other constant c2 times y, if it's c1 f of x plus c2 f of y, then it's linear. In terms of a vector field being invertible, through invertibility, well, we have the bottom here. If f of x equals ax is the linear vector field defined by a, then the following are equivalent. The determinant of a is 0, then f is not invertible, okay? F inverse, in other words, does not exist. Inverse is a -1 as an exponent. The image of the unit square will have area 0. I'll show you that. The image of the unit square collapses to either a point or a line. And f of x is not unique, right? Not a unique solution. So all of these things all mean the same thing. They're all equivalent, okay? So, well, the first type of thing you talked about in the notes this year was, finding unknown constants a and b if vector x is a times u plus b times v. So you've got your matrix A, your vectors u and v, and your vector x. So if we're writing vector x, -24 and -6, as sum a times vector u plus sum b times vector v, this is no different than the question we did earlier, right? Where we were just doing, linear combination. It's the same kind of thing. So we can just do the top, -24 is a times -8, so -8a plus 2b. The bottom is -6 equals a minus b. Times this whole equation by 2, then we can get the numbers in front of the b's to both be, well, you can make them both 2's, or in this case, I'll get a 2 and a -2. So copy down the first. The second one times 2 will be -12 is 2a minus 2b. And because they're the same, b's, right, they're both 2b's, 2 and -2. They're opposite signs, but the same number, so we can add them. If they were both positive 2b's, we'd subtract to get rid of the b. But this way we can just add. -24 plus -12 is -36. -8a plus 2a is -6a. And divide both sides by -6. And we would get a is 6. And then sub back in to get your b. Okay, so with vectors here, it's no different than the linear combination that we did before. Now in part B, though, we want to find a to the n, a to the exponent n times u plus a to the exponent n times v. So we've got the matrix A, and this was our vector u. And so here we're going to do the dot product, multiplying matrices. So row dot column. So I'm going to talk about matrices in the next one, but this was, studied in vector field, so I thought I'd do it here. So 6 times -8 is -48, plus 16 times 1 is 16. And we get 32. Multiplying here, -1 times -8 is 8, plus -4 times 1 is -4. And we get the vector 32, 4. Now, in the note that you guys had recently, talked about no 3x3 determinants, no 3x3 inverse, no dot, no cross, all of that. But also talked about matrix product, which confused me slightly because you did do products here. You also did them with Leslie matrices, like if you're talking about, juveniles and adults. So when they said matrix, matrix product, I'm not sure if they mean they're not going to ask you to do the actual product on the exam. So I'll hopefully be able to get somebody to kind of figure out what they meant by that, because you definitely, have this in your notes for sure. There's a couple of places where you have to do a product, right? So -8, 1 is called an eigenvector, right? That is associated with the lambda equals 4. If we do AV and we do the product, then we get 6 times 2 is 12, plus 16 times -1, so that's 12 minus 16 is -4. And here, -1 times 2 is -2, plus -4 times -1 is +4. So this vector is going to be an eigenvector. Now, we can use any multiple of a vector for an eigenvector. So it can be, this actual vector or any multiple of what we had, okay? We'll talk about that more tomorrow. So If I do 4 times u, my vector u is negative 8, 1. Look at what 4 times u is. 4u is going to be this negative 32, 4. That's got a negative 1. Negative 2v is going to be negative 2 times this v is negative 4, 2. What do you notice? They're the same thing, right? So AU here was negative 32, 4, and 4u is as well. And so you're going to learn that in terms of eigenvalues and eigenvectors, that AV equals lambda v for any eigenvalue lambda and any eigenvector v. So we're going to be spending a lot of time working on eigenvalues and eigenvectors tomorrow. Okay, so this was just kind of, something that they pointed out now, but it will come up again. Okay, and so we also know that if we do have, lambda as an eigenvalue and v as an eigenvector, that we can also take a to exponent nv is the same as lambda to the n times v. Okay, which is going to be a lot easier, right? Because let's face it, negative 2 to the n is a lot easier than a matrix to the n. Okay. So find the image of each of the following under the matrix A. The image of AX equals V. So we have this matrix. We call these numbers in A, B, C, D. And remember, we talk about the determinative matrix. We're going to study it tomorrow. But in a 2 by 2, you guys talked about the determinant. You just don't have to know a 3 by 3. So the 2 by 2 determinant of a matrix is 3 times 4 is 12 minus 5 times 1. So 12 minus 5, which is not 0. So in this case, the determinant is non-zero. We'll talk about, what if the determinant is 0, then the matrix won't be invertible. So in this case, if our determinant is non-zero, if we were to do the product of A times X, and X is 1, 0, then A times X is 3 plus 0. 3 times 1 plus 5 times 0 is 3. And 1 times 1 plus 4 times 0 is 1. So we get 3, 1. So if we take, the vector here, 1, 0, we get the vector 3, 1. So here's the vector 3, 1 there. And then if we take the vector 0, 1 and do AX, we've got 3 times 0 plus 5 times 1 is 5. 1 times 0 plus 4 times 1 is 4. And so we get 5, 4, which is right here. And that gives us this parallelogram. Okay. So the image here is going to be a parallelogram that's spanned by those vectors, 5, 4, and 3, 1. Now, here, if we get a parallelogram spanned by 0, 1, and 1, 0, this is just the unit square, right? So if you look at this matrix, if A is 1, 2, 1, 2, well, your determinant, AD minus BC, this time is 0. Because it's 1 times 2, which is 2, minus 1 times 2, or 2 times 1 is 2. That means it's not invertible. And remember, when we said it's not invertible, we know back from page 219, if it's not invertible, then the image of the unit square collapses to either a point or it can be a line. So in this case, on the bottom of 223, if we take A times 1, 0, we get 1, 1. A times 0, 1, we get 2, 2. And 1, 1 is just the vector from here to here. And 2, 2 is the vector from 0 from here to here. So this is just a straight line. And that's what our image is. Okay, and that's because our determinant is 0. So I know they asked a question on the final last year. That was something, I know they said to me that they had a question where they had to look at it and it was a line. It was just like this one on 223. Okay, so other vector field questions. So if we've got f of uv is defined as u plus v on top, 3u minus v on the bottom, and it's a vector field where vector x is 3, negative 3, and vector y is 0, 3. What's the first element of f of x and the second element of f of x? So if we have f, here's x, so f of 3, negative 3. So this is my u, and this is my v. So we're defining f of uv as u plus v on top, so 3 plus negative 3. And the bottom, 3u minus v. So 3 times u is 3 times 3 minus v, so it's minus negative 3 or plus 3. So that would be 0 and 9 plus 3, so 12. So the first element is there, and the second is obviously the one below it. So first is 0 and second is 12. What about if you want f of y? Well, y is 0, 3. So there's your uv. So we've got u plus v, so 0 plus 3, and then 3u, so 3 times 0 minus v. So first component is 3, and then 0 minus 3, there. So we'd have first would be 3, and second would be negative 3. Okay, so now looking at your answers there, what if we define z as a function negative 80 times vector x plus 70y? Find the first and second elements of f of z. So we already had that f of x was 0, 12, and f of y was 3, negative 3. And we're saying that z is this. So if we take f of z, we're going to get negative 80 f of x plus 70 f of y. So we have f of x, we can sub that right here, and we have f of y to put right there. So, well, the first element, we can just look at the top number, right? Can't write the word tonight. Element. There we go. So the first one, negative 80 times the top there is 0, plus 70 times the top there is 3. So that's 7 times 3 is 21, so that's 210. So what would be your second element then? Using your equation here. So we'd have negative 80 times the bottom second component is 12 plus 70 times negative 3. So 8 times 12 is 96. So that's negative 960 minus 210. So negative 1170. Okay, any questions? Okay. So here, if we have f of x, we want f of x, f of y, and then f of z. Okay, so f of uv is negative 2u plus 5v. There's vector x, there's vector y. So f of x is f of 3, negative 3. And this time it's defined as negative 2u plus 5v. Well, this top is my u and the bottom is my v. So we would just get negative 2 times 3 plus 5 times, oh, that's just 3, not negative 3. So negative 2 times 5 plus negative 2 times 3 plus 5 times the bottom is 3 as well. So negative 6 plus 15. So 9. Okay, what about f of y? What would you get? Y is the vector negative 1, 4. So go ahead, negative 2u plus 5v gives you what here? So my u is negative 1 and my v is 4. So positive 2 plus 20 or 22. Okay, so what would your formula for f of z be if this is your z? Go ahead here, what would it give us? So it'd be negative 4 f of x plus 6 f of y. Now f of x is right here, right? F of x is 9. And then we had f of y is 22. So go ahead, what would be your final answer here? Well, we'd have negative 4 times 9 plus 6 times 22. So 6 times 2, so that's 12, carry the 1, so that'd be 132. Now, if they give you direction field, they usually don't ask you to draw the direction field. Usually it's like a matching, different graphs with the different equations. I'll show you a little bit of drawing at the end tomorrow by hand. So kind of what they've asked before. But for this one, I'm just going to show you how you can check, if you've got, say, 4 graphs and you've got an equation, you have to know which one it is. So it says verify the direction for the vector negative 5, 5. So first of all, this particular function is 2x plus y and x. And if we're doing a positive run, that's to the right. A negative run is to the left. Positive rise is up and negative rise is down. So when we've got f is 2x plus y and x. So here if x is a negative 5 and y is 5. Well, that's 2 times negative 5 plus 5. And then the bottom is x, which is negative 5. Negative 10 plus 5 is negative 5, negative 5. Well, the top number is the run. So that's a negative run, which means to the left. The bottom number is our rise. Positive rise is up, so negative rise is down. So that means at x is negative 5 and y is 5, it's got to go down and left, which is like that direction. Okay. So negative 5 and 5 is right here. And take a look, right? You can see that at negative 5, 5, the arrow there is going down and left. Okay. So what you can do is find a point on all four graphs where at least a couple of the graphs are different, right? So maybe one graph at this negative 5, 5 goes down and left. One graph goes down and right. So then you can tell those two graphs apart. And then maybe you have a point over here that you test, right? And, check a point where they're different, right? Because you don't want to check, if they're all going down and left, then that's not going to help you. You're not going to be able to tell any of them apart, obviously. So for this one, if we have the function here, it's y 2x minus y. So if we're testing negative 5, 5, well, what do you got? Go ahead and sub this in. So y is 5, and then we have 2 times x, 2 times negative 5 minus 5. So 5 and negative 15. So the top number is our run. So it's positive 5, so that's to the right. And our bottom number is our rise, and it's negative. So that means it's going down and right in this region of this graph. So at negative 5, 5, in this particular vector field, it's going to go down and right. So negative 5, 5, we can check, right there. Okay, so let's see if we can match them here then. Okay, so match each vector field with the correct equation. So kind of hard, I guess, to show you, all of it at the same time, but here we've got graphs 1, 2, and 3. There's 1, 2, and 3 is up here, and then here's your equation. Okay, so if we compare some of the, points on the graphs here, so let's say I look at, a region up in here somewhere, right? So if I look at negative 4, 4, this one is going down and right. But this graph at negative 4, 4 is going down and left. So I could tell those two apart by that spot. Now sometimes maybe graph 2 and 3 would both be going down and right at that position. So you do sometimes have to do different points. This one I kind of get lucky because negative 4 and 4, this one's actually going up. So I could actually tell all three graphs apart just by testing that one point. All right, go ahead and test in all three equations and see what you can come up with here. Okay, so if we have x, y, well, that's pretty easy, right? If it's x and y and we're using negative 4, 4, then that one's got to be negative 4, 4. And then this one, well, we've got 2 times negative 4 plus 4, and then x on the bottom, negative 8 plus 4. So negative 8 plus 4 is negative 4 and negative 4. So that would be run is left, so that's left and down. This one is left and positive rise, so left and up. And then this one is y, which is 4, and then 2 times x minus y. So 4, negative 12. So positive run, so that's right, and negative rise, so right and down. So right and down is this one, that one's up and left, and that one is down and left. So we should be able to tell them all, right? So the last one here, right and down, is this one. That's graph 3. This first one, xy, is left and up. So that's graph 2. And the other one has to be 1, obviously. And if you type in, vector fields in this GeoGebra, kind of like algebra, but geo, then you can, test different vector fields there. Okay, so we'll start on one more section, which is matrices, inverses, and determinants. But again, like some of the stuff, I had to take out. So, if you see anything on a 3x3 inverse on an old exam or 3x3 determinant, then, if they gave you the determinant, they expect you to know whether it's invertible or not, but that's pretty much it, right? Okay, so G is page 232. So as far as matrices go, if you look at, the dimension of a matrix, it's the number of rows by the number of columns. So rows go this way and columns are up and down. So we have to know the dimension because we have to know when can we add matrices, when can we subtract, when can we multiply. So this is a 2-row by 1 column matrix. This one would be 2 rows by 3 columns. This is 1 by 3. This is 3 by 3, which is what we call a square matrix. And in order to calculate an inverse or determinant, we can only do that for square matrices. And this would be a 4 by 3, for instance, okay? So if we want to add or subtract matrices, they have to be exactly the same dimension. So both 2 by 2s, both 3 by 3s, etc. Okay? So matrices must be the same dimension in order to add or subtract. Okay? And it's pretty easy. We just add or subtract the number that's in the same corresponding spot. So if we take, the top left, 2 plus 2 is 4. That 4 would be what we call the 1, 1 entry of the matrix, which stands for the number that's in the first row and first column. If we take the 1 plus 5 is 6 on the top right, then that 6 would be in the 1, 2 spot, which would be first row, second column spot of the matrix. If we look in the bottom left, 6 plus 3 is 9 there. The 9 would be in the 2, 1 entry of the matrix, which would be the second row and first column spot. And the last spot, 4 plus 7 is 11, would be called the 2, 2, second row, second column. Subtracting, no different, just obviously watch your signs, right? So if you have, -4 minus -2, it's -4 plus 2, right? Otherwise, same thing. So what's your answer for 4 here if you add those quickly? So we'd have 2 plus 3 is 5, -1 plus 2 is 1, 1 plus 1 is 2, and 3 plus 4 is 7. Subtracting, same thing, just watch your signs. So go ahead and finish the bottom row. That minus that would be what? So 3 minus 3 is 0. 1 minus 2 is a -1. And -1 plus 1 would be a 0. Now, if you need to take a matrix and multiply by a constant, then you would just multiply here, -2a by every single entry. So take every number inside a and multiply them all by -2. So it's sort of like distributing. So -2 times 3 is -6. -2 times 2 is -4. -2 times 5 is -10. And -2 times 1 is -2. And to transpose a matrix is just to switch the rows and columns. You can transpose anything. You can't inverse anything. To do the inverse, we know that the determinant, of a 2 by 2 can't be 0, or the inverse doesn't exist, which we'll talk about more in a sec. You also can only inverse if it's square. Okay, so if we take both rows and make them into columns, that would be the transpose. So here, every row becomes a column. And that's our transpose. So what's C's transpose? So if we talk about, the dimension, A is 2 by 3, so A transpose is 3 by 2. 3 by 3 and 3 by 3 is obviously still 3 by 3, but a 1 by 3 would then become one column. So this is what we call a column matrix. And that would be a row matrix. So as far as matrix multiplication goes, again, I'll show you how to take a matrix and just times by one column because of, you're doing it in the Leslie matrices, which is like, if you have a juvenile and an adult, talk about that just in case. And hopefully, we can get clarification on that post on OWL just to see if you will have to do that part or not. But here, add or subtract. But if we want to multiply, the column first has to equal the rows of the second. So circle a row in the first matrix and a column in the second matrix. So if you want to do a 2 by 3 multiplied by a 3 by 4, we can do it. And the answer is a 2 by 4. The answer will be the outside numbers. Okay, but if they asked you to multiply a 2 by 3 and a 2 by 3, well, I know I can only add a 2 by 3 with a 2 by 3, but these middles don't match. The columns of the first don't match the rows of the second. If those middle numbers aren't the same, then we'd have to say we can't do it. In other words, it's undefined. So when we do it, we circle a row in the first, a column in the second, and we do the dot product, right, which is just multiplying. So 1 times 1 is 1, plus 2 times 2. 1 times 1 is 1, plus 2 times 2 is 4. So 1 plus 4 would be 5. product, we get 1 times 0 is 0, plus 2 times 1 is 2. So 0 plus 2 would be 2. In the bottom here, we get negative 3 times 1 is negative 3, plus 2 times 2 is 4. So negative 3 plus 4 would be 1. And then second row, second column, negative 3 times 0 is 0, plus 2 times 1 is 2. So 0 plus 2 is going to be 2. So what would you get here? If we do this row first, and again, you can write out your dimensions. So we've got a 2 by 2 multiplied by a 2 by 1. So our answer is 2 rows by 1 column. So 1 times 3 plus 3 times 2 is 6 plus 3 is 9. And for the bottom, we'd get what? So 2 times 3 plus 2 times 2 is 6 plus 4 is 10. And then, of course, we can do row dot column for a 3 by 3 as well. So 1 times 2 plus negative 1 times 3 plus 3 times 1. And that would be 2 minus 3 plus 3. So that's just going to be 2. So what would your middle row give you here? And again, it's a 3 by 3 and a 3 by 1. So we're going to get a 3 by 1. Okay, so 2 times 2 plus 2 times 3 plus 2 times 1, 6, 10, that's 12. And bottom, well, it's 1 times anything, right? They're all 1s. So 1 times 2 plus 1 times 3 plus 1 times 1. So I'm assuming if we do find out that you don't even have to do this simple of a product, that then if they're going to ask you, about Leslie matrices, about juveniles and adults, that maybe they're going to give you the product and then ask you to interpret it, or maybe they're not going to ask you to go from year to year, right, recursively. Maybe they'll just ask you to draw the diagram. I'll show you what that looks like tomorrow. Okay. Okay. All right. Well, I hope you learned a lot. We'll leave it there tonight. So hopefully I can find out about the multiplying and see whether we have to do, powers, because if we don't, it's one less thing to do tomorrow. Okay. So have a great night. Hang on if you have questions, and I'll see you back tomorrow, same time, same place. Okay. Take care and have a good day tomorrow. Hopefully the weather won't be so crazy. Lots of freezing rain. Hopefully it'll be sunny for once. All right. Take care, guys. Any questions? Hey, take care, everyone. See you back tomorrow.